You are beginning to get a sense that scientific notation can help you work with big numbers. Like how many millions are in a trillions? Alright, so in standard form, 1 million would be 1, and then 6 zeros.
Where's the energetic intro? Just skip.
Oh yeah, what's up? This is Mr. Sal. Thanks for watching. Don't forget to like, subscribe, and comment.
And I'm going to posted like 64 videos.
Alright, and then 1 trillion in standard form is a 1, but now with 9 zeros. Like a tease. So in scientific notation, we got 1 million, which is 1 times 10 to the 6th. 1 trillion is 1 times 10 to the power of 9er. Alright, so what we want to do is figure out how many millions are in a trillions. So what operation should we use if we want to compare these two numbers? Again, it's asking how many millions are in a trillions. That would be division.
Wait, I thought it was, no. Wait, doesn't a trillion have an extra 3 zeros?
That sounds better, yeah. Let's do that.
Woo!
Thank you.
We helped your YouTube video.
Nice.
Saved it.
Good.
I'm so proud of
Because people
myself.
are watching out there.
There we go. 12.
That's me.
Right there.
People is-
Alright, so this will be a more accurate comparison now. Write this problem out with correct operating using scientific notation. Alright, so write this problem out using scientific notation. Well, would have the trillion. So I got 1 times 10 to the 12th. And I'm going to divide this by 1 times 10 to the 6th. And this is how we would figure this out. And yes, some of you guys already figured out that it would be 1 times 10 to the 6th. That's how many millions are in a trillion. And so this would be 1 million millions in a trillions.
Wait, slow down, slow down.
Wait, slow down.
Alright, now we didn't show exactly why this is 1 times 10 to the 6th in green here. But we will. That's why it's called multiplying and dividing with scientific notation. So write down here. When numbers are written in scientific notation, the problem above can be solved rather quickly. We just kind of have to remember our exponent properties and rules. The problems below will help you practice the skills you will need to do this. You will return to the problem above on the next page. So we'll look at that. Discuss with a partner. Nope, don't do that. What properties of exponents you will use to help simplify the problems below. Use the properties to simplify each expression. Okay. So this one is the quotient rule, where we're going to take the base 10, which was there for both of these. And we got a base 10. And when we multiply bases that are the same, we add the exponent. So this is 4 plus 3, which would give us 10 to the power of 7. Now we're not worried about writing these in standard form.
I thought you were multiplying bases.
Alright, so how do we get 10 times 10 is 10 to the 7th instead of 100? Because if we expand these, let's say 10 to the 4th, this would be 4 tens multiplied together. And then we're going to multiply this by 3 tens over here. 3 more. So that's what exponents are, is just repeated multiplication. So we have a base of 10, but how many do we have? 7 of them.
So you're just making another.
Alright, good luck.
So what I did was I did -3, and then I added it to 5, and then I got 2. So now it'd be 10 to the power of 2, which equals 100.
Correct. Excellent, Bert. Alright, this is the quotient rule for exponents. So we do have the same base on it, these 10. But right here, since we are dividing the bases that are the same, we will subtract the exponents. So 6 minus 3 is 3.
I understand it now.
Alright, now I'm going to show this expanded just because some of you guys are still like, what? So I got 10 6s in the numerator, which is what that exponent is telling me. 10 of these. And then in the denominator, I've got 3 of these. And we can see that these 3 cancel out, leaving me with just these 3 tens 10 to the third. Good luck.
Yo, what's up, YouTube? Your boy. We gotta do this problem. Okay, so I'm gonna write this in expanded form. 10 times 10 times 10 times 10 times 10 times 10. Hold on, wait. Over 10 times 10 times 10. Don't question my intellect. Times 10 times 10. So we can pretty much just cancel all these out. That, and that gives us 10 by the power of -2. That is a 10. And I have superior intellect.
No, he did a great job. So that would be expanding all of these, which we don't necessarily need to do, but you can, all right, if it helps you. So let's show this a little bit differently. So I do have my base 10 values on these, so I'm going to take my base 10. And since it's division, we are subtracting the exponent. So 4 minus 6. So that would be 10 to the power of that -2, which was shown right account. All right, discuss this problem with the class. Nope. We're going to write our thoughts below. Okay, we will do that though. So 5 times 3 times 2 times 8. If we solve this one just straight across, it may cause some problems because the order of operations would make us 15 times 16. But we can change things a lot right account. Because everything is multiplication, we can make it, this is really 5 times 3 times 2 times 8. But since it's all multiplication, I can rearrange these, which is the commutative property multiplication. So I can make this 3 times 8 times 5 times 2. And then I can reassociate these. So that's the association property, like these. The reason I would want to do that is because I'd have 5 times 2, which is 10. 3 times 8 is 24. Now 24 times 10 is a little bit easier to do. And that would give us 240.
Yeah. Which is 2.4 times 10.
Now here's the thing is since this is all multiplication, when we see this in scientific notation, that means we can move the stuff around, which is why we saw specifically on those last 4 parts base 10 values. Because if I can move the base 10s together, then I'm just adding, because this would be multiplication, I'd be adding the exponents. We're going to rewrite this problem like the problem above. And that's what I was saying. We're going to group the powers of 10, and then we're going to group the other 2 decimals together, and then we'll just multiply them, all right? So once again, the first thing I would want to do is just move the decimals close together. So I'd have 5.1. So let's rewrite this as a full multiplication problem first, okay? Times 6.8 times 10 to the third. So I'm going to move the 5.1 and multiply the 6.8 first. And then I'll be multiplying that by base 10 to the power of 5 times base 10 to the power of 3. So again, I've just commuted these and moved them closer together so I can have some similar bases closer together. Next, I've got 5.1 times 6.8. So that's 34.68. And then when I combine these, I've got base 10, but I've got that 5 plus 3 right now. So that will end up being a 10 to the power of 8. And this now is 34.68. But this right here is still not formal scientific notation. So what I need to do is make this big number smaller by a place value of 1. So that'd be 3.468. And I'm going to multiply this by 10. But the power changes. So I made that big number smaller, so I got to make the exponent bigger by 1. So that now is to the power of 9.
Times 10 to the power.
So if you did do this, because it didn't specify specifically on this, it will on the test though. Yeah, you could have had 3,468,000,000. Something like this, yeah. It's the same thing. We'll use the same method on these two problems. Alright, so on this one, once again, if I ignore those parentheses altogether, that would be considered okay. So if I change this out like these. And what I would need after that is just some kind of multiplication between the 10 squared and the 3.5. Alright, now that I have these, again, I'm going to move similar terms next to each other. So I'm going to take the 6.9er and multiply this by the 3.5. And I'll multiply this by 10 to the power of 2. And we'll multiply that by 10 to the power of 5. Alright, well then we'll do 6.9er times 3.5. So that'd be 24.15. Using my exponent rules right here. I have 10 to the power of 2, and then the 2 plus 5 though. So this would be 10 to the power of 7, and I got 24.15 multiplied by these. Well, this of course is not the solution, which is what we want. What I need to do is move the decimal one place to the left, 2.415. Now again, I took 24 and made it 2.4, so that made it smaller, which means I need to make my exponent bigger by one place value. So this would be multiplied by 10 to the power of 8. This one just says to solve. Alright, good luck.
Okay, first you have to change the parentheses. Times 2.4. Times 10. Power of 3 times 10 to the power of 6. Then if you combine these, it's 4.56 times. Oh wait, and then you gotta do these together, which is 10 to the power of 3 plus 6, which is actually, oh whoops. And then cut down, and it's 4.56, because you don't have to move any decimals, times 10 to the power of 9.
Oh, this is easy.
That is correct.
Next one is can I do the next one?
Good luck.
Okay. Because this is division. Well, what I did, so you would subtract these right here. So this would be 10 to the power of 3, and then because this is division, you would divide these, and that would equal 2. So.
Oh, I did do that.
That's it.
Wait, so I answered the entire
That's all we
problem into the
needed to do.
calculator, and it was like 20,000.
Find each product or quotient on this one. So, again, we are dividing on these. So, I can split this up, and I do have my base 10s. This is the first part I'm going to start with. And I've got 3 minus 7 on this one. So that'll give me 10 to the power of negative 4. Then I've got 2.3958 divided by 1.98. So that's 1.21 times 10 to the power of 3 minus 7. We don't need to move the decimal on that one, so it's just going to remain this way.
I have a question. What should we round the decimal to?
Alright, what about at these? So, once again, I'll rearrange these. So I got 7 times 3.5. And then we'll multiply the base 10 values. There's more. 10 to the power of 5 times 10 to the power of negative 3. And 7 times 3.5.
Wait, would you?
And then we'll multiply this by 10. And I'm going to add the exponents. So 5 plus negative 3,
Which is actually
which would
just
give me
5
10 to the
minus
power
3.
of 2, because that is 5 minus 3, really.
Oh.
But now I've got, this is not formal scientific notation still. So I do need to move the decimal one place to the left. So I'm making that big number smaller, so I'll have to make the exponent bigger. So I end up with 10 to the power of 3, 2.45 times 10 to the power of 3. On this one, we're going to split these up again. I'm going to look at my base 10 value. So I got 10 to the power of 8 minus 3, which would be 10 to the power of 5. But when I divide the 3.006 and the 7.3, yeah, we're going to get this decimal 0.411. But again, this is still not in formal scientific notation. So I'll have that 0.411 times 10 to the power of 5. But I need to move this decimal to the right one place. So I'm going to make that small decimal bigger. So I got to make my exponent smaller by 1. So this would be 4.11 times 10 to the power of 4 now. And that is the answer. Alright, good luck.
So what I did, I used the fishy method, I guess. So because 40% is over 100, so it's 40 over 100.
Oh, I forgot.
And then for 140 million. And what's 40% of that? So that'd be X. That'd be, and then, yeah. Okay, and so what you do, you would do, I gosh, so you'd start down here, so it'd be, okay, and then you times that by 40, then divide by 100.
Fishy method.
And then that would equal 56 million. Okay.
I swear I have all passes in my book.
Okay.
Alright,
Sorry.
Alright, that's an excellent use of the percent proportion. Now, this 56 million did want us to write this answer in scientific notation. So that would be what?
5.6 times 10 to the power of 4.
No,
I just did that in my head.
10 to the power of 6.
Oh, 7.
7.
Power of 7.
Oh,
I did
oh,
that in
yeah.
right now.
Yeah, because we got the 6 zeros, and then we got to do the 6 as well. So the final answer there, yep, 5.6 times 10 to the power of 7. Excellent work.
Damn.
I need help with D.
Now there's a couple ways we could do G. We could change the 30 into scientific notation. Or we could change the scientific notation, 1.2 times 10 to the 5th, into standard
Let's do
notation.
that.
But since we're working with scientific notation, I'm going to change 30 into scientific notation.
Well, it's 100.
So this would be 3 times 10 to the 1th. So that is 10 to the power of negative 4 now. Alright. Alright, then I do 3 divided by 1.2. So that's 2.5 times that stuff. So we're going to keep that. And that also gives us formal scientific notation right there. Return back to the problem at the beginning of the section if we want to figure out how many millions are in a trillion, which we did already. What operation will help us achieve this? We already saw that that would be division. Use the method discovered above to perform this operation. Alright, so we would have had 1 trillion, which is 1 times 10 to the 12th. And we'd be dividing that by 1 million, which is 1 times 10 to the 6th. So using this same technique, we'd have 1 divided by 1, which is 1. Alright, then we got base 10s. That's 10 to the power of 12 minus 6. So 1 times that stuff. So that gives me 1 times base 10, 12 minus 6, bam, 6. That's what we got on that problem as well. So, how many thousands are in a trillion? 1 million. It didn't say thousand, it was millions before.
Oh, there's million thousands?
I guess we can try that one. B is different then.
That's good.
So if there's a million millions in a trillion, then how many thousands are in a trillion?
There's 1 million.
There'd be 1 billion.
That makes a little
1
sense.
billion thousands in a trillion. That'd be one. That's insane.
What is 3 millionths multiplied by 7 ten-thousandths? Alright, so let's look at the decimals on it, these. 3 millionths would be 0.10 hundredths thousandths, 10 thousandths, 100 thousandths, million. So we got 3 of those millionths. And then this is going to be multiplied by 7 ten-thousandths, so 7 10 hundredths thousandths, and 7 ten-thousandths right here. So let's go ahead and change these into scientific notation. So this one would be 3 times 10 to the power negative 6. And we're going to be multiplying this one by 7 times 10 to the power of negative 4. So we'll rearrange these. I got 3 times 7 times 10 to the power of negative 6 times 10 to the power of negative 4. Whatever. Alright. Well, 3 times 7 is 21.
Wait, how'd you come out with?
Alright, so I got 21, and this is going to be multiplied by 10 to the power, and I'd have negative 6 plus negative 4.
But then how did you get the 10 to the power?
Alright, well, this gives us 10 to the power of negative 10. And I got 21 times that garbage. Well, the 21 has a decimal in the wrong place, so as it turns out, we're going to need to make that number just a little bit smaller into a 2.1. Yeah, so that now is 2.1. And since I made that number smaller, I'm going to have to make the exponent 1 bigger. So that's 10 now to the power of negative 9er. That's it. Alright, on this one, E, we got 562.1. That is not in scientific notation, but we can easily change it into scientific notation. 5.621. And this would be multiplied by 10 to the power of negative 2. Alright, so I got 3.1 times 10 to the power of negative 3 times this garbage. So we'll rearrange the numbers. So I got 3.1 times 5.621. And this is all multiplied by my base 10s, 10 to the power of negative 3 times 10 to the power of 2. And 3.1 times 5.621. Alright, so we have that product. But now we got to work with those exponents. So this is still multiplied by 10 to the power of negative 3, but I'm going to add that 2 up in here. And now I still got my 17.4251 times now 10 to the power of negative 1. Well, this one we don't have formal scientific notation just yet. See, we need the decimal to be between the 1 and the 7 right account. So I should have 1.74251. And this I would multiply by, if I looked at the power of 10, since I moved the decimal and made the number smaller, I would have to make the exponent bigger. So 10 to the power of 0, which is okay. I'm okay if you make that your answer. Some of you guys know that 10 to the power of 0 is 1. So the actual answer could just be 1.74251. But they probably do want this in scientific notation, so we should probably just keep it like this. Alright, H right here. I'm going to show this one a little bit differently. So what I'm going to do is I'm going to take the two numbers I have, and I've only got one base 10 value, that's okay. So I can take 5 and multiply this by 0.4, and then just multiply this by 10 to the power of 5. See, I mean, you could change 0.4 into scientific notation, but I can do 5 times 0.4 directly, which as it turns out is 2. Well, that'd be 2 times 10 to the power of 5. Done. So if you change the 0.4 into a decimal, you should have gotten 4. See, because I'm making that small number bigger, so I got to make the exponent of 10 smaller into the negative. So when I combine that -1 with the 5, yes, I get 4, but then I'd have 20 times 10 to the power of 4. I still got to move the decimal over one place to make it 10 to the power of 5. What percent of 1.3 times 10 to the 6th is 6.5 times 10 to the 5th? All right. Okay, so I like to set up the proportion on these. Yeah, we got to be especially careful on this one because of how it divides. So the percent proportion looks like these. So we always have 100 right here. The percent is always above the 100, but we don't know what that is, which is what we're solving for on these. Now, again, you guys probably don't remember this, but the is number is the part, and the whole is the of number, which is in the bottom right here. And we can see that it says what percent of 1.3 times 10 to the 6th, so that's where that goes, times 10 to the 6th, is, and that's where the numerator is, 6.5 times 10 to the 5th. Is of. Then to solve these, all I would use is fish method. So I'd go down to 100, come up to times 6.5 times 10 to the 5th, and then I would divide that by 1.3 times 10 to the 6th. And that's going to equal my x, which is the actual percent on this. Well, we could do that in a calculator. We could work with them directly as well. That's okay. So if I multiply 100 times 6.5 times 10 to the 5th, I get 6.5 times 10 to the 7th. But I would still need to divide that by 1.3 times 10 to the 6th. That will tell me x. So this appears to be, so when I combine these, I got 10 to the 1th. So that's 5 times 10 to the 1th. Done. In the world, approximately 1,146,000,000 people speak Chinese as their first language, while 341 million speak English as their first language. Approximately how many times more people speak Chinese than English as their first language? All right, so we're going to divide these two. So we're going to take I'm going to change that into scientific notation. 1.146 times 10 to the power of 9. And I'm going to divide this by 3.41 times 10 to the power of 8. So from here, we can see that my base 10, 9 minus 8 is 1. Then I got 1.146 divided by 3.41. All right, I'll use 3 decimal places on that. So you need to move this decimal over 1, which means I need to subtract 1 off my exponent, giving me, in scientific notation, 3.36 times 10 to the power of 0, which would mean that there's 3.36 times as many people that speak Chinese than English. That's not a 0. That's not a 6. It's a 0. A millipede's leg is 4.23 times 10 to the negative 3 centimeters long. How long is the millipede's leg in standard form? So the negative tells us we'll move the decimal 3 times to the left. So that would be 0.00423 in, I guess that'd still be centimeters. Despite its name, a millipede does not really have 1,000 legs. If it did, what would the length be if you could line up all the legs of a 1,000 leg millipede. So there'd be 1,000 of those 0.00423 centimeters. So it's really 0.00423, and there'd be 1,000 of them, so we can just multiply that by 1,000. Now, some of you guys see that that's 10 to the power of 3. So that would be 4.23 centimeters. Almost a yard.
That's not even.
It'd be more like maybe an inch or two.
scary bill.
The thickness of a dollar bill is pretty small, but the thickness of a dime is also pretty small. How many times thicker is the dime compared to a dollar bill? So we're going to take the dime and divide it by the dollar bill, by the way. But the dollar bill, alright, so the dollar bill in scientific notation, 1.0922 times 10 to the power of negative 2 in centimeters. I get that negative 2 because I had to move the decimal 2 times. And I'm making the small number big, so I got to make the exponent smaller. Alright, now that's the dollar bill. Let's look at the dime. Changing this one into scientific notation, I'd have 1.35. Again, I made that decimal value bigger, so I got to make the exponent smaller. And this one also is in centimeters. Now, since we want to know how many times bigger the dime is than the dollar bill in thickness, I'm going to divide these two. So I have this division problem now. And I got 1.3 divided by 1.0922. That gives me a really long decimal, but I'm only going to write a few of the numbers. 1.236. And this is multiplied by 10. I got negative 1 minus negative 2, which would be a 1. Because I got negative 1 minus negative 2. So that changed the operation to plus. Well, that's how many times bigger it is. If we change this to standard form, you'd have 12.36 times.
Are we doing 13 and 14?
I guess bigger. A cricket weighs that many ounces. How many crickets are in a pound? Which has 16 ounces. Alright, so we got to take 16 ounces and divide this by 3.8. 8 times 10 to the power of negative 2. That will tell us how many of the crickets would be in those 16 ounces. And we are comparing now ounces to ounces. So I can make this 16 times 10 to the power of 0 if I want to make it extremely convenient. So I would have 16 divided by 3.88. So rounding that gives us 4.12. And this would be multiplied by, I'd have 10 to the power of 0 minus negative 2, which really gives me 10 to the power of 2.
And how do you know?
Alright, so that would be, if I change this in standard form, 412 crickets.